All right, so with my very Springfield hat, my I Miss Abe, we're taking a look at chemical energy. We are writing what is in orange today. That's what we're taking a look at here. We are going to have a couple of videos we're going to take a look at. First one, I'm going to let you watch this on your own. You'll click this link. It's in your particular notes. I don't want any potential copyright issues with me showing someone else's video, so I'm going to let you watch that on your own. So you can take a pause right here. Okay, welcome back. Now that you've taken a look at that, we should know. Let me get me out of the way. Energy stored in bonds of chemical compounds. Those are atoms and molecules. Atoms are individual elements as they break down, and the molecules are multiple atoms together, whether the same compound or a chemical compound. Usually, once chemical energy is released from a substance, that substance is transformed to an entirely new substance. So, for example, you drink a can of Pepsi Cola. After you drink it, because that is a chemical compound of its own, now it's something else. It's calories inside your body. It turns into energies. It's a totally different thing. So that's what's going on with that. Okay, example we have here besides the Pepsi Cola one that I already did. Dry wood is full of potential chemical energy. As it burns, the fireplace, chemical energy is released. So it's kinetic. We talked a lot about kinetic and potential energy. Kinetic energy, the potential chemical energy. So that's the stored chemical energy of the firewood. The kinetic is motion. So in this case, the chemical energy being released is kinetic energy being released. It's converted to thermal energy, heat, and light energy. So that's why you can see when you sit by a fire. The wood now turns into ashes and smoke. Smoke goes up the chimney. The ashes lay down in the bottom of the fireplace. Those are completely new substances. So that's what's going on with that. Okay, exothermic. It's when heat is released. Sorry, I keep flying around the screen. When heat is released during a chemical reaction. And then endothermic, and I'm going to review like how to remember these in just a second. When a chemical reaction happens and heat is absorbed. So exo, think of an exit. So that's the release. When you exit a room, you are leaving the room. Exothermic, leaving. Endo means in. So like if you've ever heard endocrine medicine, it's internal medicine. And so that is what's going on with that. That's the inside. Really, if you can remember that exo, exit, is external, is outside, then you're going to be good. Since exo means exit, so when heat is released, endo, it's when heat comes in. Trying to help you guys remember these things easily. We're going to take a look at a baking soda and vinegar experiment here, trying to figure out which is going on. Is it exothermic energy or endothermic energy? So we're going to take a look at that lab on, I'm going to get the answer here, and we're going to take a look at the lab. So baking soda and vinegar is going to be an endothermic. Sorry, I'm thinking of a different lab. Baking soda and vinegar is going to be an endothermic because this is on the snap sheet. We saw the little like Alka-Seltzer tab, and it has stuff coming out of it. It's the same thing we did when we had that balloon experiment where the balloon was on top of iced tea bottles. Dumped something from the balloon in. A lot of you said you dumped a white substance into the water. It was actually baking soda and vinegar. Some of you knew that already anyhow, so you did really well with that. It's an endothermic. Heat is taken from the surrounding air, even when it's inside the bottle, for that example we used in class, to help build the new connections. Just like moving from one medium to the next in a wave changing speeds, endothermic reactions worked the same. The air changed temperatures, so it speeds up or slows down based on the medium it travels through. Now, you have all these notes on your screen, obviously, anyhow, because you have the opportunity to take notes on Google Classroom on the slideshow. If you want to take them on paper, that's fine as well, though. I'm not trying to limit the way you can do things. Okay, so food and your body. So I've got chemical covered up a little bit, but I think we can kind of read what's going on here. Food is a good example of stored chemical energy. Talked about this with the example of the can of Pepsi Cola. As the bonds between these atoms break, chemical reaction occurs, new compounds are created. When the bonds break or loosen again, oxidation occurs almost instantly. Oxidation means adding oxygen to it. It's how we breathe. It's how we actually manage to move around. And it also is how other things happen that you see on an everyday basis. We're going to talk about a couple of those here in these notes. So what is oxidation? This video here kind of gets into the explanation specifically. I am going to go ahead and play this one because as you can see, I'm going to show it to the 1 minute and 20-second mark. So I'm going to go ahead and click this link. You guys can follow along here on the screen. Okay, and 1 minute, 20 seconds. Quick thing about it. Okay, so this, I know we haven't done a ton here, really looking at the periodic table. What this is looking at, these, I should have circled with the mouse. These that are circled, they're going to lose electrons easier because they have fewer electrons there. As we move to the right across the periodic table, they are more balanced with their electrons. Notice one of those is oxygen, so that kind of makes sense. Okay, we're going to stop that there. It's asking me questions, and I knew it was going to do that. I was planning on stopping it there. We're going to go back into our notes here and blow this back up so we can see it. So that's what we just looked at there. This helps explain what oxidation. This helps explain what oxidation is specifically, and I believe that it did. It gave us a good couple of examples. You should hopefully better understand it. So we're going to keep going. To clarify, oxidation takes place when an atom or compound loses one or more um, electrons. I'm not sure why it says one or more electrons. I'll get that fixed. Some elements are more prone to oxidation rust than others, and I talked about that in the video. So this is just to clarify part and get into details on it. So why should we care about chemical energy? Not just because it's the unit that we're in, but we actually have a point to it. So let's take a look at that. In real life, it's all around us. You use it daily when you eat, walk, use anything with a battery, including your phone, etc. So if you remember that your body breaks down the food you eat, your body uses about 75% of the food breakdown to function. We should know from sixth grade science when we looked at those energy webs or the energy flow diagrams how energy reduces as you go up the energy flow chart. But in this particular case, so we do have where the energy does get used, body breaks down the food that we eat. The body uses about 75% of that food breakdown to function. The rest is broken down, goes into either fat or thermal energy. So basically, if you eat too much, then it turns into fat or it turns into heat. And the heat is why you see people sometimes get sweaty if they eat too much, have like a bunch of soup, something like that. So that's what's going on. Okay, gonna take a short break there. The experiment that you're doing here is already linked in here. I'm about to run out of time on this video, so I'm gonna go ahead and just kind of get to the what happened right here. I do want you to take a look at that experiment and try to understand that. And hopefully all of this makes sense. If you had any questions on it, definitely let me know. Thanks so much.